Here's Mr. Scott Hanson's talk about AI in microwatts, kilobytes, and megahertz, lessons from real AI deployments at the endpoint. Please.
Yeah, thank you for having me. So as I mentioned, I'm founder and CTO at Ambiq. Ambiq was a company that was founded a little more than 10 years ago with the goal of putting intelligence everywhere, putting intelligence in our clothing, in the walls in the building around us, in every bridge, in every car. And increasingly putting intelligence everywhere means deep neural networks, means AI everywhere. And so I want to talk today about some of the challenges we've seen in making that happen. And as we'll talk about, when you try and take a cloud's worth of compute and compress it into microwatts, kilobytes, megahertz, when you've got resource constraints, it's actually quite difficult. Now, the good news is these are problems that have been largely solved. What I want to do today is walk you through some of the lessons we've learned. Hopefully, you walk away feeling that this is something that is quite achievable, and hopefully Ambiq is a key part of that. So we've of course heard all of the news about cloud-based large language models. We just heard a good talk from Intel about large language models. It's all worth the hype, but for me, if that's all we focus on, we're missing actually the bigger AI story. And that story is that there are billions upon billions of devices that are everywhere that are all starting to use inference for all sorts of interesting purposes. And some of them are directly tied to those cloud-based large language models. Large language models sit in the cloud. They're trained on print data and internet stored data. They're not seeing and hearing everything that's going on around us. All of these billions of devices, whether it's your smartwatch or it's your doorbell or any number of other devices, these are collecting real-time data. They can be fed back to the cloud-based large language models. And these devices themselves are actually becoming quite intelligent. So whether it's your smart doorbell that's identifying not just that there's motion at the front door, but who came, when they came, and what they were doing, or it's your wrist-based wearable device that's telling you what your sleep quality is like, what you can do to improve your future sleep quality, et cetera. These are amazing opportunities. Now, the challenge, of course, is what I alluded to earlier. You've got a cloud's worth of compute that we're trying to do in endpoint devices, what we call endpoint devices. These are devices that have 2,000 times less memory available. You've got, this is maybe a bit pedestrian to consider, but you've got a price budget that's 3,000 times lower. I can't spend $30,000 on the latest NVIDIA GPU. Maybe I've got $15 of total bill of materials available. And the most important one, from my perspective, the most challenging constraint is the energy one. I'm going from a wall plug device that can consume kilowatts to something that maybe consumes milliwatts or microwatts on a battery. So we're talking about 100,000 times less power budget available. So the question becomes, how do you build devices that can achieve the performance required here, but can do so in this tiny little power budget? That's where Ambiq comes in, and that's what I founded the company to do. Admittedly, not initially to target inference as a key use case, but intelligence broadly. To date, we have enabled more than 230 million smart devices. These are devices that are wrist-worn. These are devices that you carry in your pocket, smart credit cards. My guess is many of you either have one of our chips or have used one of our chips. And what is unique about our chips is that they consume far less power than anything else out there. And the way they do that is using a technique that's decades old called subthreshold and near-threshold computing. For those of you that don't know about this, the basic idea is in conventional digital computing, we represent digital information in zeros and ones. Digital 0 is maybe 0 volts. Digital 1 is some higher voltage, 0.8 volts, 1 volt, 1.2 volts. The problem with that is the higher the voltage, the more energy we spend. Energy is voltage squared, so as voltage goes up, I'm getting a pretty dramatic increase in energy. So therein lies an opportunity. If I can drop the voltage, I can save a lot of energy. If you drop the voltage so far that you're not actually turning on the underlying transistor, you're in what's called the subthreshold region. If you go a little bit above that turn-on voltage of the transistor, you're in the near-threshold region. At Ambiq, we make use of both operating modes. And the great thing about what we do is it's a technology platform, and it's applicable to a lot of different circuit types. We can build digital circuits, we can build analog circuits, we can build MCUs, MPUs, AI accelerators. I have a guy on my team building delta sigma converters for audio use cases. The challenges with operating at such low voltage are significant. Okay, so you become exponentially sensitive to temperature variations, to voltage variations, to manufacturing variations. The good news is this is what we solve at Ambiq. It's the reason other companies don't tend to chase this mode, but we've taken on that set of challenges and we've developed a platform that we call SPOT, Subthreshold Power Optimized Technologies. What that is just a whole set of techniques, architectural techniques, production test techniques, runtime circuit adaptation techniques that allow us to deal with these variations. And we've used that technology to build a bunch of products. We've got some timing chips, and our flagship products are a family of microprocessors called Apollo. So we've had 5 generations of Apollo. We're actually here at the show this week launching our new Apollo 5 family, which you can stop by and learn more about. But this is a technology platform at this point that's covered by a whole range of patents, and we deliver dramatically lower power. So we tend to see 3 to 10 times better energy efficiency than our competitors. In an industry where 10% better generally is pretty good, that's a pretty big differentiator. And when you're thinking about trying to do more with your silicon, you're trying to do more compute, more, in this case, edge inference, endpoint inference, that's a big deal. So as I mentioned, we're here launching our newest product, Apollo 510, which is part of the new Apollo 5 family. It's the first member of many that will come. This is by far the most ambitious product we've ever built. It is the fastest, it's the lowest power, and very importantly, it's tuned from the start to run inference and all the other tasks that you need to run in an endpoint AI application. I'm not going to get into great detail about what this is. You can come by our booth that I'll point you to later and learn more, but it's based on the Cortex M55 processor. So this is a wonderful, lightweight but extremely powerful processor. It's got a vector unit that can do as many as 8 multiply accumulate operations per cycle. That's great for traditional signal processing, so get rid of your DSP, use this. It's great for inference. Get rid of your specialized accelerator and use this. It's got a ton of memory. Okay, so I think everybody would be quick to tell you that in a deeply embedded application, memory power, very critical. Memory performance, very critical. The more memory you can get, the better. If there's one thing I've learned over the years of building this company, it's that our customers have an insatiable appetite for MIPS, so for clock cycles, and for memory. So the more memory we give them, the more memory they can use. This chip has everything you need for an embedded application. We have a 2.5D GPU, so you always have some kind of UI use case. There's a display. There's an expectation that these displays look and feel like your phone, despite the fact that it's a tiny little watch or it's a thermostat. It has to look and feel like your phone. And so we've been very focused on providing a great experience there. And every conceivable peripheral you want. You've got ADCs. We've got digital interfaces for NAND flash, for NOR flash, for digital sensors, et cetera. So for me, I have to step back. I founded the company. As I look back, I'm astounded at how far we've come. So if I look at our first generation Apollo, this was about 10 years ago. It was a Cortex M4, still a very powerful platform. It's one that we ship a lot of, the Cortex M4-based devices, and it ran at 24 megahertz, which at the time was plenty of bandwidth for the types of applications we were chasing. Today, Apollo 510 runs more than 10 times faster, plus it's got the M55, which is a more powerful platform. We've also got more than 10x the memory. Okay, so I mentioned earlier, customers have this insatiable appetite for memory. Most importantly, AI performance is between 20 and 90 times better for AI workloads relative to the original Apollo. And that comes with, despite the higher performance, comes with 5 to 25 times better energy efficiency. So we have an abundance of performance, we have an abundance of energy efficiency available. Now truly is the time for endpoint AI. Okay, it started as a whole bunch of signal processing that our customers were doing, but increasingly that's become deep neural networks, and we have a platform here that's well suited to that. I see a lot of talk about AI use cases that are hypothetical. We're out there right now engaging our customers. They're building real use cases. So what I hope to bring you today for the remainder of this presentation is real insights that comes from our customers' real use cases. And I'm going to say that the majority of our customers today are doing what I call small AI. Okay, this is where you're taking an algorithm that's maybe a traditional algorithm, maybe it's a filter-based algorithm, or it's using traditional signal processing techniques, and you're replacing that with a deep neural network. Okay, it's not the sexiest thing, but what you get out of it is you get better performance, right? And in many cases, our customers don't even advertise it. Just magically, the spec sheet for their product shows better performance. They don't disclose why. It's things like heart health analysis. We have a large number of consumer wearables. I'm wearing a couple of our customers' products right now. Heart health analysis, fitness analysis, sleep quality analysis, these are all shifting to neural network-based approaches. We see a lot of audio use cases, so speech enhancement. That can be done using traditional algorithms. It just turns out that deep neural networks are quite good at this particular task. What we're also seeing, though, is that our customers are using these so-called small AI use cases as stepping stones to big AI. These are things that look more like what you might do in the cloud. I use the example here of natural language processing. So traditional natural language processing says I can talk to a machine in a way that I would talk to my wife or my son or my colleague. Now, I've specifically put the qualifier of narrow natural language processing. If I'm talking to a watch or a thermostat or whatever, I don't need to support every known language construct. I don't need to recite Shakespeare to this thing. I needed to understand the 100 commands that you would give to a watch or to a thermostat. And there might be 10 different ways to say those different commands, but you can talk naturally. That's something that is now achievable. We are today, if you look at Apollo 5, it's not specifically focused on imaging, but there are an amazing number of imaging use cases that have popped up. So object detection being a great one. We have customers in the smart doorbell space. And in that space, you can imagine you've got a big applications processor that consumes a lot of power. You do not want to power that thing up. It's going to dim the lights in the room. You want to have a coprocessor that's doing that work, doing basic object detection that says, hey, I think it's time for you to wake up and do the big processing. That's what neural networks in these so-called big AI use cases can do. So 7 years ago or so is when our customers started developing neural networks on Apollo. And at the time, it felt very scary. It felt unachievable, and there were really two major challenges that we were seeing. The first of those is there was a lot of friction in the development flow. Most people probably know about TensorFlow. Google has this great training framework. There is, in fact, a version of that called TensorFlow Lite Micro that allows us to compile networks for microcontrollers. The problem is there's a pretty big gap between that and bare metal microcontroller, right? There's a whole big gap that has to be filled, and there's traditionally has been a lot of friction in filling that gap. And then the other thing is of course, power inefficiency, right? We have had many customers tell us that, hey, when I go from running a traditional algorithm to replacing that with a deep neural network, suddenly power goes way up, the processing workload goes way up, and that's a problem, okay? Now, of course, I'm here to tell you Ambiq has got you covered on that front, so don't worry about that, we'll take care of you. And in fact, we've also covered this friction problem too. We have, I'm not gonna go through all the boxes on this slide, but we have a product that we call Neural Spot. This is our AI software development kit to sit between that TensorFlow layer and the bare metal silicon. It includes a whole bunch of utilities. It's also paired with a model zoo that contains what we call AI development kits. These are pre-trained neural networks that we developed in-house. We give you the training data, we give you the model itself, we give you weights, we give you all the instructions you need to get going, all the documentation. You can go to GitHub today and you can pull the code and it's all freely available for you. So when you pull all that down, you're able to follow the full neural network development flow quite easily. So again, I'm not going to walk you through the boxes here, but we've got the model zoo, we've got Neural Spot, and then we've got the whole TensorFlow framework that allows you to get down to bits that will actually run on a microcontroller. We give you everything you need to iterate through this flow, and once you've been through it once or twice, it's actually quite simple. So I want to give you a couple lessons from our experience doing neural networks at the customer. And I'm going to say right now, it hasn't been a linear process, right? Again, 7 years ago-ish when we started engaging customers on this front, it felt scary. And so my first lesson is this, it's that you too can develop and deploy AI at the endpoint. You don't need a team full of PhDs. It felt that way at first, but you don't. You don't need to even significantly depart from the traditional embedded development process that you're used to. We provide all the software that you need to get going. If you can follow a basic software guideline, if you can listen to YouTube videos, you can do what we do. And there's also this perception that you need a cloud's worth of compute to train these models. But these models aren't that big, right? I have a guy on my team who is training multi-megabyte models, and he's doing so with a consumer gaming desktop PC. This is at this point, like an 8-year-old gaming PC. There's nothing special about it. You don't need a cloud's worth of compute. And then to top it all off, there's a bunch of great software tools out there that can help you. So I was just talking yesterday to the guys at Edge Impulse. They have a great product that fills this gap and makes this all easy. So between what we provide, what some of these other companies provide, it's very straightforward to go develop AI today. So the next lesson that I have extracted over the years is don't spend time on crazy hardware architectures. There's some really innovative and cool work out there on compute and memory solutions, on novel accelerator architectures. But the fact is, what you really need is you need an easy-to-use platform that is efficient. And you need to pair that with well-designed networks, well-designed software. We actually spend a lot of time at the network level. There's so much you can do in cutting out layers, experimenting with different model types. And that has a much bigger impact on the energy usage, on the resource usage, et cetera. And what I'm actually showing here is some, let's call it obfuscated information from an internal study we did on speech enhancement. So what we did is we looked at 4 different models, and we were, for our own purposes, looking at having models that could run on our smallest, lightest weight microcontrollers on up to the most complex ones. And so we experimented with a variety of different architectures. And some of these were published works that we pulled off the shelf. Others were complete custom designs. And what we did is we kind of dialed up and down the sizes of these things. So you can see that the largest models on the left, Model 1, about 2.6 megabytes worth of weights, down to our smallest model, Model 4, about 80 kilobytes worth of weights. And you can see a commensurate reduction in the total operation count. And you go from needing 2.7 gigacycles per second to run this thing streaming to down to less than 25 megacycles. And most importantly, what we're looking at is we're looking at performance. So this overall MOS it's a mean opinion score. It's basically, it tells you how good the speech enhancement sounds. Higher is better. And so you're paying a penalty by going to fewer parameters. The accuracy drops. But if you were to listen to these wave files that come out of this, you would say, you know what, actually these sounds pretty good. That's a reasonable trade-off. And so the point is, we got so much, we got a 100x difference in the number of cycles required, and thus the amount of energy required, just by tweaking the network architecture. So spend time there, okay? Now, the next point is it's not just network architecture, it's also software. So the software that comes out of the various compilers, it works, it doesn't always work well. And this table I'm showing here shows the number of cycles that we spent on one of the networks from the previous slide. And we were seeing performance that wasn't matching our expectation. Okay, it was underperforming, it was running at a much lower frame rate than we expected. We had to really dig in. We had to actually go in and profile this thing, and we had to look at, and in this particular case, the red outline layers should have been basically minimal contributors. And once we dug in, once we did some basic profiling, we found, oh, this is easily fixed. We went and rewrote some of these functions. And we're still a little bit in the Wild West in that there are a lot of functions like that need to be rewritten, they need to be tuned to your model. But this is not hard. And so I would say, really focus on profiling. Apollo 5, with the Cortex M55, has some amazing profiling tools. You can find out how many vector instructions have been run. You can find out what cache hit and miss statistics are like. You need to study all these things. And we make all that very easy for our customers to do. And I would strongly encourage you to do that. I see among customers and even among some of our own internal engineers, they have a tendency to skip that step. They think everything looks good. They kind of trust the underlying tools. Don't trust the tools. Go look at it yourself. Fourth lesson, this is 4th out of 5, we're almost done. Start with small AI and go to big AI. It feels intimidating, but if you just start with replacing an algorithm that you've already got, if you take an algorithm that's based on traditional signal processing, upgrade it to using inference, that's it. That's a good first step. You've got a golden model, you've got a new one, you can compare the two results. Good news is, with Apollo's energy efficiency, the energy overhead of doing that is going to be pretty minimal. So at this point, there's endless data showing that neural networks are basically outperforming traditional signal processing algorithms. They're outperforming humans. There was famously a whole lot of work in the computer vision space around some of the computer vision contests and showing that neural networks ultimately won. The same is true across audio and biosignal analysis and all of this. And so if you are not replacing your traditional algorithms with neural networks, I would strongly suggest that you reconsider that. It's not that hard these days to get after this problem, okay? It in years past felt like you needed a team of data scientists. No longer true. And then the final thing I'll say is this. For all the attention we give to inference, it's just one tiny piece of the pie, right? There's this tendency to say, I need an amazing NPU, and I need this, and I need that. That's one piece of the pie, but there's so many other things you have to pay attention to. There's the sensing. I'm bringing data into the chip. The sensors themselves consume power. There's sensor interfaces. There's ADCs. There's I/O circuitry. There's pre-processing. I can't get away from doing, for the most part, general signal processing. I have to do maybe some FFTs or some other computations. Then you've got inference, but you've also got an operating system. You've got security. Adding sensors and cameras and microphones everywhere freaks people out. Okay, so security has suddenly become a really top concern. You spend a lot of your resource there as well. Graphics and UI. You've got displays. You've got speakers and microphones. Data storage, right? I mentioned memory is a big constraint. There's communications. There's power management. You have to do all that well. We at Ambiq, of course, have a platform that allows us to do all that well. And so I would encourage you to make sure that whatever you're doing, don't lose sight of the broader system puzzle. In these endpoint applications, we don't have the luxury of having a single chip inference accelerator and multiple chips that all can work together. There's one chip that does everything. Our VP of AI, Carlos, likes to say that AI is a feature. It's not a product. Okay, and that's how we treat it here. It's one piece of the overall pie. So with all that said, I hope you walk away with the feeling that AI at the endpoint has traditionally been challenging. It's something that is now quite achievable. If you want to learn more about Apollo 510, which is the new product, come see us. We're at Hall 3, booth 301 with Top Electronics. Have a number of demos of our multiple generations of Apollo. We're at the ARM booth. Come by and see that there. So that's it. I appreciate your attention. I'm happy to answer any questions there might be.